Differentiation is also often useful when we try and sketch a curve. Now, sketching a curve, well, we can type it into some computer algebra package and get some nice output. But really, quite often, all we're interested in is just getting some idea of what the function looks like. We don't want to fire up a computer, get it to boot up, and get the program working and stuff. We just wanted to have a little quick sketch. Of course, one way we can do is just to choose a few values and to plot the curve, to plot some points. But then we might miss some interesting behaviour if the points that we're choosing are some way away from interesting things, or if there's something interesting happening in between our points, which we somehow miss. Before we do that, let's actually summarise some basic properties of graphs and of sketching graphs. To make sure you understand these, maybe you could draw or plot the graphs in the case of some simple function, y equals x plus 1 or something. If we're given a function f and a non-zero real number a, then the graph y equals f of x plus a is the graph of y equals fx shifted upwards, so in the positive y direction, by a distance of a. The graph of y equals f of x minus a is the graph of y equals fx shifted in the positive x direction by a distance of a again, so it's shifted towards the right. If a is greater than 0, then the graph of y equals a times f of x is the graph y equals fx, but stretched in the positive y direction by a factor of a. And in the same sort of way, if a is greater than 0, then the graph of y equals f of ax is the graph of y equals fx, stretched in the positive x direction by a factor of 1 over a. Or if you like, it's contracted by a factor of a. And the graph of y equals minus f of x is the same as the graph of y equals fx, but it's reflected in the x-axis. And the graph of y equals f of minus x is the graph of f of x, but reflected in the y-axis. If you're given a function, y equals f of x, then one reasonable way of trying to understand it is to plot some points. And this works well for quite a lot of very simple functions. So linear functions, quadratic functions. So as an exercise, you might like to plot the points on y equals x cubed as x goes, say, from integers minus 3 up to plus 3. So minus 3, minus 2, minus 1, 0, 1, 2, and 3. And then you join the points with a smooth curve. That'll give you a pretty good idea of what the function looks like. The only thing is, you don't really know what the behaviour looks like at 0. Is the graph completely flat? It looks reasonably flat, but is it actually, is the gradient 0? You can't see that just from plotting points. What we want to do to really understand a function properly is to understand much more about it. We want to understand its stationary points, we want to understand whether they're maximum points or minimum points. We want to understand much more about the function. So here are a few interesting features which I think you should think about when you're sketching a curve. So firstly, are there any values of x where the function is not defined? So for example, when y equals 1 over x, then that's not defined at x equals 0. Something funny is happening there. So this is called the domain of the function. It's all the points where the function is defined. Then next, you should work out, if you can, where the function crosses the x-axis, which means that you should solve if f of x equals 0. Now, that might be quite hard to do algebraically, but you might be able to get some kind of idea by some numerical calculations. And where the graph crosses the y-axis. Of course, the graph crosses the y-axis just at the point f of 0. You should find the stationary points and work out whether they're maxima or minima or something else. So you should determine the nature of the stationary points. You should work out how the function behaves as x goes towards plus or minus infinity. Is there some asymptotic behaviour that starts to become really dominant when x is a large value? And then you should think about the behaviour of the function near points where it's not defined. So here's an example. So sketch y equals f of x, where f of x is 3x to the power 5 minus 5x cubed. I've chosen this to be fairly nice, but it'll still reflect most of the ideas that we've seen. So, first of all, are there any values of x where it's not defined? Well, no. If I give you any x, you can work out what f of x is going to be. So if x is 5, you can plug in x equals 5 and get a value out. And it's not like 1 over x when you plug in 0, something funny happens. So, firstly, it's defined everywhere. Where does it cross the axes? Well, where is f of x equals 0? So f of x equals 0 when this thing here is 0. So we can take a factor of x cubed out. And this is naught when x is 0 or when this bracket here is 0. And 3x squared equals 5 when x is plus or minus the square root of 5/3. Now let's think about the stationary points. What's f dash of x? Well, f dash of x is 15x to the 4 minus 15x squared. So again, we're using our rule that when we differentiate x to the power n, we get n times x to the n minus 1. And f dash of x equals 0 when 15x to the 4 minus 15x squared is 0. Well, that's 15 times x squared minus 1 equals 0. And that happens when x is 0 or plus or minus 1. What do the stationary points here look like? Well, we can work out f double dash very easily as well. F double dash of x. So again, we're differentiating x to the n is nx to the n minus 1. We get 60x cubed minus 30x. So at x equals 0, f double dash is 0. At x equals 1, f double dash of x is 60 times 1 minus 30 times 1, 30. So that's positive. And at x equals minus 1, f double dash of x is minus 60 plus 30, that's minus 30, which is negative. Now remember that if f double dash is negative, that means that f dash is decreasing. So we're starting out being a positive and decreasing towards 0 and going and ending up with a negative. So that happens at a maximum. And when f double dash is positive, that happens at a minimum. And f double dash equals to 0 needs more thought. Or if you like, we can choose a very small positive value of x and a very small negative value of x. X equals a half or minus a half or something, and just see whether you get something positive or negative. And what happens near infinity? Well, as x gets really big, this x to the 5 term is much larger than the x cubed term. So if you like near infinity, it starts looking much more like 3x to the 5. So with all these things in mind, we can try sketching a graph. I haven't quite left myself a huge amount of room, but never mind. I think it's probably enough. So, first of all, f of x equals 0 at 0 and plus or minus 5/3. Plus or minus the square root of 5/3. 5/3 is a bit bigger than 1, and the square root's also a bit bigger than 1, be about 1.3 or something. So 1.3 and minus 1.3-ish. So these are really at the root of 5/3, and minus the root of 5/3, and at 0. Where does it cross the y-axis? Well, f of 0 is 0, so that was easy. So where are the minima and maxima? Well, the stationary points. So at 0, it's flat. That's a stationary point. At x equals 1, so what's the value of the function? Perhaps I should have done this before. So at x equals 1, y is 3 minus 5 or minus 2. And at x equals minus 1, y is minus 3 plus 5 or plus 2. So we can plot some points. So at 1, so remember that the square root of 5/3 is a little bit bigger than 1, so 1 is in between these. So we have 1 here, and it has the value of minus 2. And this is a minimum, so either side of this it's increasing. At minus 1, it has the value of plus 2, which in fact is opposite, so it will be something like this. And it's again flat because it's a stationary point, and this is a maximum. So it goes down on either side. So the graph is going to look something like this. We're just going to have all the features here. And then we can try and join these with a smooth curve. Let's draw this in yellow. So it's flat. It clearly has to go down towards this minimum here, and then it has to go fairly sharply up to be 0 there. Again, it's flat here, has to go up to here, and then sharply down. And then either side, as x gets really big, go really fast, it's clearly going off to infinity very fast, and eventually it's going to look more like x to the 5 than x cubed.